We're going to look at solutions to a very particular type of question known as the roots of unity. So they're the solutions to a simple equation, z to the power of n equals 1, or sometimes it might equal -1. Now when you plot these solutions, something lovely happens. If you were to join all the solutions up, you get a lovely polygon, an n-sided polygon. So it depends, what sort of root you're trying to find. The vertices will all lie on the unit circle because it's equaling 1, the modulus is 1. So let's do the fifth root to unity. So z to the power of 5 is equal to 1. And so we saw using derivatives, we can say that's cis 2 pi k plus, well in this case 0, because the argument of 1 is 0, divided by 5. 1 is a real number, so I know I'm going to get conjugate pairs. So I've chosen 0 plus or minus 1 plus or minus 2. So we get cis 0, which is 1, and then cis 2 pi and 5 minus 2 pi and 5, 4 pi and 5, and minus 4 pi and 5. So if we were to place them, with something like this, it's great because z to the power of 5 equals 1. Well, you know 1's a solution to that because 1 to the power of 5, of course, is 1. So you can plot 1, but then you know they're evenly spaced. So the next one would be cis 2 pi on 5. Its conjugate must be there. So there's minus 2 pi on 5. Go round at another 2 pi on 5. We get cis 4 pi on 5. Its conjugate must be there. There's cis minus 4 pi on 5. And we get a pentagon, which lies on the unit circle. So still working with the fifth roots of unity. We're saying that omega, or w, depending on how you want to read that, is a complex root of z to the power of 5 minus 1 equals 0. Same equation, we've just moved the 1 to the other side. Show that omega squared, cubed, power of 4 and power of 5 will be the other solutions, or the other roots. Now, thing to keep in mind here, when they say it's a complex root, it means the one that's not real. So we know that 1 would be a solution, but they're not talking about that one. So z to the power of 5 is equal to 1, but we know if w is a solution, then w to the power of 5 must be 1. Well, w to the power of 5 to the power of 5 would be 1 to the power of 5, which is 1. So w to the power of 5 must also be a solution. Well, guess what? I can keep doing this. W squared to the power of 5 is the same as saying w to the power of 5 squared. Well, w to the power of 5 is 1, and 1 squared is 1, so w squared is a solution. Well, w cubed to the power of 5. Well, I can play around with the indices and rewrite that as w to the power of 5 to the power of 3. W to the power of 5 is 1, 1 cubed is 1, so w cubed is a solution. Well, w to the power of 4 to the power of 5, I could rewrite as w to the power of 5 to the power of 4. W to the power of 5 is 1, 1 to the power of 4 is 1, therefore w to the power of 4 is a solution. So we've now shown that the other solutions are w to the power of 2, 3, 4 and 5. Thank goodness the power wasn't any bigger. There's a much quicker way of doing it. Do it this way. So z to the power of 5 is equal to 1. Essentially, we're going to do exactly the same thing, but in a smarter way. Okay, so we start off the same. Well, if w is a solution, then we know w to the power of 5 is 1. Starts off exactly the same. If k is some integer, then w to the power of k to the power of 5 can be rewritten as w to the power of 5 to the power of k. Well, w to the power of 5 is 1, so we get 1 to the power of k, which is always 1. So I only have to do it once now, because I now substitute in for k, and I get all the solutions. In fact, I don't have to stop at w to the power of 5. W to the power of 6 is a solution. 7 is, 8, 9, 10. Any integer you like will be a solution to this. Prove that if I add 1, omega, omega squared, omega cubed, omega power of 4, we get 0. There's several ways you can do this. First way is really quick. So it's solutions to a polynomial. So I can say this is the sum of all the roots. We just found that these were the 5 roots. So the sum of the roots would be minus b on a. But remember the equation was z to the power of 5 minus 1 equals 0. So b is actually 0 by the sum of the roots. But then I want to prove 1. So how did I get 1? Well, because w to the power of 5 is equal to 1. That's how I can say that. There's one way of doing it, sum of the roots. Another way, remember we sub it in, it will solve the equation, so I know omega to the power of 5 minus 1 is equal to 0. That would factorise like so. Remember, if you have omega to the power of n minus 1 is equal to 0, the first factor is always w minus 1, and then the factors will go power of w going down by 1, so n minus 1, then n minus 2, then n minus 3, then n minus 4, all the way down, and eventually you get to 1. Well, it must be that 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0, because we said omega was not equal to 1. So that first factor can't produce the solution omega equals 1. It's not a possible solution. Therefore, that first factor can't be 0. It must be the other factor that is 0. Of course, another way we could do it. That looks familiar. It's a geometric series. So I've got the first term is 1, the ratio is omega, number of terms is 5. So a, r to the power of n minus 1 over r minus 1, sub in, omega to the power of 5 minus 1, hang on a sec, that's equal to 0. So we have our solution. So lots of different ways of solving. But once we've done that, it now wants us to find a quadratic equation. But the roots are going to be a combination of these ones. So omega plus omega to the power of 4 will be one root, and omega squared plus omega cubed will be the other root. Sum of the roots will be omega plus omega to the power of 4 plus omega squared plus omega cubed. But we now know 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. Therefore, that must equal negative 1. Okay, we've got the sum of the roots. Product of the roots. Expand that out. I can tidy that up though. Because remember, omega to the power of 5 is equal to 1. So I could rewrite omega to the power of 6 as omega. And I could rewrite omega to the power of 7 as omega squared. That once again is equal to minus 1. So my equation, x squared minus the sum of the roots, so we get plus x, plus the product of the roots, minus 1. We have our equation. Going to a cube root of unity this time. We're not going to prove it again. Use the fact that 1 plus omega squared is equal to 0. What would 1 plus omega squared to the power of 3 be? Now you could expand the whole thing out, but I'm not going to. 1 plus omega squared would be minus omega if I play around with that result. Minus omega to the power of 3 is minus omega cubed. Omega cubed is equal to 1. So most of these problems we only need two facts. Omega to the power of n, whatever the power is equal to 1, or minus 1 if it was the other case. And that 1 plus omega squared plus omega, and so on up to n minus 1 is equal to 0. Using those two things, we should be able to solve the problem. Evaluate. 1 on 1 plus omega plus 1 on 1 plus omega squared. Yes, I could get a common denominator and do all that, but I'm going to tidy up the denominators. Because 1 plus omega I could rewrite as minus omega squared, and 1 plus omega squared I could rewrite as minus omega. And that's an easier fraction to work out. I end up with minus 1 minus omega on omega squared. But minus 1 minus omega is omega squared. So the answer is 1. We're now going to create a cubic equation. The roots are 1 plus omega, 1 plus omega squared. Well, straight away I know one factor because we've got the roots 1, so it can be z minus 1. Then I'll form a quadratic with the other two. So same idea as I did with the quadratic before. I know it's going to be z squared minus the sum of the roots. So that'll be 1 plus omega plus 1 plus omega squared, so I get 2 plus omega squared, plus the product of the roots, which turns out to be 1 plus omega squared plus omega cubed. Alright, so let's tidy that up, because remember, we know 1 plus omega squared is equal to 0. So 2 plus omega squared must be equal to 1. And 1 plus omega squared plus omega cubed must be equal to omega cubed, but omega cubed is equal to 1. So we get z minus 1 z squared minus z plus 1 is equal to 0. I suppose that is an equation, but hey, let's have some fun. Expand it out. Collect like terms. Z cubed minus 2z squared plus 2z minus 1 is equal to 0. Solve this equation. Whenever you see an equation like this, notice all the coefficients are 1, and we're just going up by irregular amounts. It looks something like this, but I'm just missing the factor out the front of z minus 1. So it looks like that. Now I know the solutions to z to the power of 6 is equal to 1, because that's our roots of unity. It'll be 2 pi k on 6, where k is plus or minus 1, plus or minus 2, and 3. But I want to solve this equation. Well, let's turn it into something we already know the answers to. If I multiply top and bottom by z minus 1, the top of the fraction becomes z to the power of 6 minus 1. They're the ones I already know the answer to. And when you're solving a fraction equaling 0, it's the top of the fraction you solve. Here though, z can't equal 1, because it would mean we'd have 0 on the bottom of the fraction. So it means we've got a pentic equation there, power of 5. So there are only 5 solutions. We've turned it into z to the power of 6 equals 1, which has 6 solutions. So my solutions are all of those solutions less one of them. And the one we don't use is the one that makes the bottom of the fraction equaling 0. So we'll have all of those except z equals 1, which means the answer to this equation, we have cis plus or minus pi and 3, plus or minus 2 pi and 3, and also cis pi. We can work those out because they're nice exact values, and there they are. A very old paper now. Here's one that came from 96, the 9th roots of unity. But they've told us which one is going to be w. So it's going to be 2 pi 9 plus I sine 2 pi 9. Show that omega to the power of k is a solution of z to the power of 9 minus 1 equals 0. So z to the power of 9 is equal to 1. So it's cis 2 pi k on 9, where k equals, I don't know why I didn't bother with conjugates on this one, but it doesn't matter. 0, 1, 2, 3, 4, 5, 6, 7, 8. But have a look at what we got. 2 pi k on 9, which I could rewrite using Dual's theorem as cis 2 pi on 9 to the power of k. Well, cis 2 pi on 9, that's what they told me omega was. So I get omega to the power of k, where k is 0, 1, 2, 3, 4, an integer. Prove that. Oh my goodness. But really, it's just the same question again. They've rewritten it. They put the 1 over the other side, but it's still 1 plus omega squared plus omega cubed, and so on and so on and so on. So z to the power of 9 minus 1 is equal to 0. I'm just going to do it the quick way. Sum of the roots, so that equals 0. Therefore, I can move the 1 over, and I've got their expression. Hence, go and show this result. Well, I've just done a little bit of factorising. Every one of those will create a linear factor, z minus the root. So that's all I've done there. I've rewritten it with 9 linear factors. You'll notice I've done something strange though. Instead of going 1, 2, 3, 4, 5, 6, 7, 8, 9, I've gone 1, 8, 2, 7, 3, 6, 4, 5. Have a look at each pair. What do you notice? Power of 1 times power of 8 would give you power of 9. Power of 2, power of 7, power of 9. Power of 3, power of 6, power of 9. Power of 4, power of 5, power of 9. And someone mentioned conjugates, and that's true. What happens with these roots of unity, when it's equal to 1 anyway, is that if you match those powers up, so the two powers add together to give whatever n is, they will be conjugates of each other. So when I just create quadratics using those two factors, I'm going to get minus the sum of the roots. But if I've got conjugates, that's going to be twice the real part. So I get twice cos, in the first one, 2 pi on 9. In the second pairing, I get twice cos 4 pi on 9. In the third pairing, twice cos 6 pi on 9. In the fourth pairing, twice cos 8 pi on 9. Okay. Product of the roots, real part squared plus the imaginary part squared. Sine squared plus cos squared, 1. So we get 1, 1, 1, 1, 1 in all of them. One of those I'm going to change because we know the exact value. Cos 6 pi on 9, well 6 pi on 9 is 2 pi on 3. The cos of 2 pi on 3 is, we're in the second quadrant, minus a half. Minus 2 times minus a half plus 1. So I've changed that one. Okay, we're trying to get this product. Gosh, we've got a product already when you look at it. But they have 3 terms. Just look at one of those parentheses with a cos in it. How could I turn those 3 things into one thing? By a substitution. I'm going to let z equal something, and it will turn 3 terms into 1. And I'll give you a hint, it's the middle term we'll be left with. In other words, z squared plus 1 will disappear. I. If you make z equal to I, z squared plus 1 will disappear because it's equal to 0. So let z equal I. We will have I to the power of 9 minus 1 is equal to I minus 1, but then in the second factor, z squared plus 1 disappear. Next one, z squared plus 1 disappear. Next one, and so on and so on. I am left with this expression here. I now have a product of single terms. Oh, except for that pesky I minus 1 there. But hang on a sec. I to the power of 9 and I minus 1 will cancel with the I minus 1 on the other one. And the other thing I've then done is there's a factor of I in each of those parentheses. So I times I times I times I, we have I to the power of 4. If I take the negatives out as well, I've got negative times negative, which is negative. We're getting closer to what we want. Let's cancel those I minus 1s. I to the power of 4 is 1. I've moved the negative over there. We now have negative 1 is 2 times 2 times 2, 8. Cos 2 pi on 9, cos 4 pi on 9, cos 8 pi on 9. We are so close, but we're still not there. They wanted cos pi on 9. We've got cos 8 pi on 9. 8 pi on 9. It's obtuse. It's in the second quadrant. The equivalent acute angle, negative 1 is 8 cos 2 pi on 9, cos 4 pi on 9 times minus cos pi on 9. We have our answer. The product is equal to 1/8. Let's play with some of these roots of unity questions. Yeah?